Good. Hello, everybody. This is Professor Ma, and this is the introductions, the sections on polar coordinates and the graphs and the equations and the graphs. To specify locations we need to do two things. We need to find a point of origin we agree upon. And we need to fix the directions. So if you are in the wilderness, you can use a tree and so fix the directions. And in the rectangular coordinate system, then we'll say, oh, that's called the x-axis. Okay, so here's a tree. Okay, top of the tree. And then perpendicular to the origin, we call the y-axis. And then we specify a location point P. I think, okay, you walk out in the x direction certain numbers A, and then you walk perpendicular to distance B. And then this is the location AB, P. Okay. But there is another way to do this. And actually the bees do them, okay? And supposedly the bees is something similar. The bees tell each other if they find a source of honey, flowers, and they will dance and fly back to the hives and dance and indicate the directions of the flowers, and then also convey how much distance it's supposed to be. And that's essentially polar coordinates. So in a sense, bees use polar coordinates, okay? So what is polar coordinates? We fix the directions, remember, on origins and directions. And then what we do is we specify the locations by two things: the angle it makes with the direction axis, the x-axis if you like, and then the distance you have to travel up. So this pair, r theta, is the so-called polar coordinates of the points. So both are ways of specifying locations. So r theta in the polar coordinates P, and there's the r, and there's the theta. Okay, and I superimpose the xy coordinates onto it. So these are two different systems: the xy system, the rectangular systems, and the polar systems. And of course, then the point P have representation in both systems. It could, the pair of number could be expressed in the address in the rectangular system or in r theta. So here are the conversion. So all we have to do is complete right triangles, then with x's are cosine theta and y's are sine theta. And these conversion rules, you just have to say it to yourself a dozen times until you just lock into your brain. So xr cosine, yr sine, xr cosine, yr sine, xr cosine, yr sine, xr cosine, yr sine. Okay, in there. Okay, the rest is easy. And then the Pythagorean theorem tells you r square root equals y square. Then we have this tangent theta. I can recover the theta in my drawing. That is, if the theta is in 0 to 90 degrees, because tangent theta, I can use the inverse tangent to find it. However, suppose the point is in the third quadrant, okay? Then the theta we talked about is this theta. Suppose I want to recover these thetas, okay? But notice, by the way, there are a couple of ways I can specify the theta to be this angle. There's nothing wrong with it. I can use negative angle to specify the directions. Okay, in this point, that's where the rectangular and polar coordinates are different. But we'll talk about that in a second. But anyway, back to the third quadrant. Suppose a point P is in the third quadrant. then it's a little more difficult to recover the angle theta because you cannot directly use an inverse trig functions. It won't give you the answers. This in that in the range. Okay, the output of inverse trig is between usually between pi and minus pi and stuff like that. Okay, so in other words, what's the moral of the story? Moral of the story, if you need to find the angles, point P in third in this location, you might want to consider its reflection across in the first and figure out what that is, and put over some tricks like that, some ad hoc methods. Okay, instead of directly getting it. Okay, now let's take a look at polar equations. In the rectangular coordinate system, we have the XY equations, okay? And X represent remember, the horizontal displacement, Y represent the vertical displacements to locate the point. So on picture, it looks like that. So the equation X equal to Y means you walk the same horizontally and then you walk up vertically, same distance to wind up at the point where X equal to Y, a particular point. But the equations R equal to theta say something completely different, even though if I don't look at the picture and I don't tell you what system it is in, and you look at these two equations and there's really no difference. It's just one variable is equal to the other variable. It could be U equal to V, W equal to S. Then you have to say, wait a minute, U equal to V in which system? W equal to S in polar or in rectangular system? Just make sure you have that clarified, because it says something totally different. This says distance to the point. It's the same as the angle theta. Angle theta, is from 0 to pi and stuff like that. Yes, exactly. If the angle measure, so here's the pictures. For instance, here you start with 0, 0. If angle theta is 0, it's theta 0, then R is 0. Okay. Theta 0, okay. And this point is, well, now theta is pi over 2, the angle, right, 90 degrees. And pi over 2 is approximately 1.7. So the distance R is roughly 1.7 something, Okay. This is the polar coordinate. Okay. In polar coordinates, then when theta goes all the way to pi, so this is the point in polar coordinates is pi, and how far out pi, that distance is roughly 3.14 in the pi direction. Okay, in the 180 degree, approximately 3.14, so something. Yeah. Clean it up and do right. Roughly 3.14 something in the angle pi theta. Okay. And you can get, of course, you can get the coordinate of that point. Coordinate of that point is 0, 1.7, the pi over 2. Okay. This is the rectangular coordinates. Okay. Now, let's take a look at the graph of some of these equations that using the letter R and theta. Okay, and let's start out with the easiest one, the constant functions. So, R equal to a constant, the distance fixed. What's theta? Theta could be anything. So, theta from 0 to pi, it goes around the circle once. Okay, constant measure distance is some constants. How about theta is a constant? Theta is the angle. If theta is constant, that means the angle doesn't change. You say, how about the distance? Which point? How far is the point in the theta directions? Could be any distance. So you get an entire line that making the angle theta with the x-axis. Okay. Notice we are using negative r for directions going backward. Okay, so for example, if this point is equal to 1 pi over 4, okay, I can then represent this point as -1, but in the same direction, pi over 4. Okay. So if I'm establishing that directions, then the opposite end pointing the same main. So in the opposite direction, I use negative sign for the r. So that allowed us to use negative r's. What else? Constant time sines or constant time cosine in this case. So let's just start plotting it, and I'm not going to go through the every one of them. You can read them through, so, or make a table and calculate the r, plot them. Okay, and keep going. Let's okay, keep plotting them. Oh, now the r is negative. Notice 120 degree. 120 degree is in this direction. Okay, but r is negative, so therefore the point plot is right here. Go backward. In other words, the negative y are going to give me the bottom three. And when it gets to 180 degree, then it makes a complete circle. If I continue on, then r become negative, then it loops around again. So in other words, as the angle goes from 0 to 2 pi, the circle is circled around twice. Okay, for cosine theta. And say, wait a minute, how do you know it's a circle? Okay, there's no, what's the geometric base for a circle? Well, here, it's just a couple of justifications. Let me blow it up. Okay, so let's say this point over here. From here to here is r. That's what I want to know, and this is the angle theta, right? And I make a connection from here to there. And from geometry, no, this is a right triangle. Okay. Within a semicircle from here to here, from here to here, this angle is always a right triangle. Okay. Why? Because it faces the other half of the other. It's true geometry. So if you peel your hair, look at that for a while, you say, oh, yes, it's equal to 3 times cosine theta. Okay, so that's why we get this formula. Okay. Or else we can algebraically use the conversion rule, and usually if you see r and r can be converted, r cosine theta becomes x. Multiply, if I see cosine theta, I multiply an extra r into it because r cosine is x, right? R cosine x, r sine y. And so I get these equations. And then if I complete the square, then I get exactly this equation of the circle. So actually this is exactly halfway is the center. Okay, and then the radius of this is 0.2. Okay. Now, if I change plus minus using cosine and sine, and then what I get are these 4 circles. I leave up to you figure out which is which and which way the curve is formed. Okay, and I leave it to you to read these. Okay, very easy to figure out. Now to figure out which way it is, plug in some number, like for instance, plug in theta equal to 0. Okay, cosine 0 is equal to 1. So then the point must be D0. Okay, 0, so D0. So it must be this one or that one. So cosine must be these two. And the other is sine. You can just check the endpoints first. Okay, so here's sines is up, cosines right, left, and this is the weight starting point from theta 0. This is where the dots is. Okay, those color dots. Now, 1 plus cosine theta. Oh, here the 1 minus cosine theta. Again, let me start it out with making a table. Then I notice cosine theta over here. So it's a even function. In other words, cosine theta is equal to cosine minus theta. So the bottom half of this curve is the same as top half. 0 to minus 180 degree happens the same 0 to 180 degree. So all I have to do is do the top half. Okay, and so I'm going to make a table. And here they are. Excuse me. Okay, now the bottom half is the mirror image. And this is called the cardioid, the heart shape. And the cardioids, for instance, it's a very interesting curve. For instance, it's the same as if I were to rotate the green circles, keep the blue circle fixed. I roll the green circles around it. I just roll it, but I keep track of my eyes on the red dots where it goes. And now I keep rolling around the blue circle, and until you get back to exactly the same point started. The same circle, same size. So the red dots will go back where it started. The track of the red dots from some cardioids. Another interesting fact about cardioids is the outline of the envelope of a series of circles, series is just a lot of circles that passes through some fixed point O. So I'm going to draw a bunch of circles, go through O, but its center sits on another circle. What does it mean? Here's a circle K. So there, I draw a circle. Okay, and how do I draw that circle, that teeny weeny circle? Oh, its center is on the blue circle. Now I keep going out, make a center and draw a circle that's do the same thing. The center is on the blue line. Then I go out a little further, make the center goes out a little further. I keep doing these, keep doing that. And if I keep filling up all the circles with center at K, the last one I draw, the biggest one is this red one because the center is right there and it goes up there, it makes a circle and as far as it can go with the center on the blue circle. And what we get is the cardioids. And this is also important in acoustics. That is the microphone. There's good simulation for the volumes that it can receive if you put a specific type of mic and pointing in that direction. Okay, and then basically if you're behind the mic, you cannot hear the voice goes up, but depends on where you are. Okay, and this is the what we call the same volume, like singing, we receive the same. Okay, so cardioids are interesting. To generalize cardioids a little bit, I can talk about function of these types. That is, instead of 1 plus minus cosine, put a constant over there, K in the front. For example, I will just draw some. Now this is 1 minus cosine. And here's the picture for 1 minus half cosine. You say, wait a minute, what happened in the middle? Oh, because this number is so small, less than 1. So this back over here is always smaller than 1. Okay, which means 1 minus this quantity is always positive. It doesn't go through the origin. So therefore, in each direction, the I is always positive. It doesn't double back and do anything like that. Okay. Because 1/2 times cosine is smaller than a half, no bigger than a half. So you cannot make that number negative. So therefore, the points, no points pass through the origins. But on the other hand, if you make the number bigger than 1, then we got in the following situation. This is that, for instance, let me start with cosine 0. If you plug in 0, suddenly find out the I is -1. So if you plot it out to pi/2, you get that. How do you get that? Oh, because let's do this. If I were to put an absolute value around it, then I is always positive. Then I will get this one. Okay. But now, because everything's negative, therefore every point is reflect across. Okay, so therefore I get that stretch for angle from 0 to pi/3. Okay. I'd like to check that. That is, if you ignore the negative sign from 0 to pi/3, you will get this curve. But because everything is negative, you have to switch every point, flip it across into the third quadrant. That's why you get a little piece. Okay. And if you continue down from pi/3 to 2 pi/2, and then it loops up. Okay, it's 0 to pi/3, and then pi/2. Then once get to pi. And I'd like to check if I continue to do that. And now there's a little loopy loop. When these things with more than 1, so you're subtracting, when 1 minus 2 can be negative, then you're going to get this loop. Okay, that's when k is more than 1. Okay, so here are some pictures of it. Okay, you start 1/4. Okay, so in other words, this is at least 1/4. 1 minus a quarter is at least 3/4. So that point is 0 degree, but I 3/4. Whoops. Okay, R 3/4, 3/4, 0. That point. 1 minus 1/4. That's now the point 0, 1/2 on the side. Now 0, 0. Now it's not looping. Okay. So we also have the roses. Okay. But 2 types. Well, basically sines and cosine. Okay. And cosine, if we look at a sine, corresponding sine, it's going to become this double the amount of petals as opposed to cosines. Okay. You got this pattern here. And so you notice that for the cosine, it is for the odd angle, the number of petals are exactly the same number as these are numbers. But if the cosine even angles, and suddenly you get twice as many petals. And you also notice there's no with 2 petals, and there's just one with 3 petals, and then one with 4 petals, 5 petals, and there's no petal with 6. Here's 1, 7, and here's A, and where's 9 is over here. And they're missing some petals anyway. Where are those ones? Well, Those are the absolute value of cosine. The reason why cosine and the sine of even angles is because the following things. Let's look at sine of 3 theta. Okay. If I put absolute value sign around it, I will get 6 petals. However, if I remove the absolute value sign, and then some of these sign will be a negative value. Therefore, some of the petals are flipped across. Okay, it's folding into only 3 petals. In other words, you traverse 3 petals twice, and that's what the 6 petals are. So if I want the 6 petals, I will put absolute value on it. Then I will get all 6 petals. Okay, so that's what the number of roses in such matters. Right. So here's a way of showing how it is sketched. Spirals. Okay, spiral is a function where f theta just increasing or decreasing. So I could say that we already did that, and we did the middle portion of it. This is called the Archimedes spiral. It's the spiral you make with a rope. Because the distance from here are fixed between the 2 runs. Okay. And when I plug in the equation for the spirals, I get this xy equation, but this xy equation, if I use cosine inverse, I only recover a particular portions of this, only from 0 to pi, cosine inverse. Yeah. So, right. So for the other equation of, if I need the equation of xy, I need to throw in a constant term to get the other pieces. Depending on what n is, I will get different pieces along here, here, and I will get them in pi value of time, depending on what n is. Now we have the logarithmic spiral, or the exponential spiral, if you like. And these are very interesting spirals because they have the property, if I draw a tangent to the radius, the tangent angle to the radius stays the same. And this is the reason why we see these things in nature. Okay, because usually in biology, when you grow, you have the fixed shell that's already grown up to this point, and then you got the shell that will try to the shell try to grow, and then the cells line up. It's at a fixed angle. You protrude, you will protrude out at the same angle every time. Hence, you get this spiral. Okay. Then finally, a little bit about rotations. If I change theta to theta minus pi rho force minus, then we rotate counterclockwise. Okay. And if I multiply by a constant to the formula cosine, that I will stretch the r out. Like for instance, if I multiply by 2r, then it stretch out. So if I look at that equations, the circle rotated to pi over 4. Okay, we started with cosine was here, right? Okay, then you rotate x to pi over 4 to that directions. And then I'm going to extend everybody twice as far. It's just radially from the center. Okay, then this will be the circle we get. Okay, so this is a summary about polar coordinates. Okay, bye-bye. Until next time. Okay, stop. Bye-bye.